right, good morning, chemists. We'll get started. So as always, starting off with a couple of announcements before we start dimensional analysis, which is the last section of chapter 1, which honestly, in terms of your scientific career, dimensional analysis is one of the most powerful, useful skills that you'll use. And I have a very specific way I show how to do dimensional analysis, and if you drink my Kool-Aid today, you'll see that you never have to memorize an equation as long as you're clever with units. Anyway, so some announcements. Do grab those chapter 2 slides. I updated them on Monday. So if you downloaded them previously, do download them again. I actually posted some pre-filled in slides there as well. So I have the blanks already filled in, but we can work through the questions together. And this is just to expedite chapter 2 to make sure that we get everything in before our first midterm exam in about a week and a half. Chapter 1 homework will be due on Sunday at midnight. And I'll just reiterate that late policy, it's only individual questions that are penalized if submitted late. So if you complete everything except one question and leave it for office hours next week, only that one question will be given that late penalty. You'll still earn the majority of the points for that homework set as long as you handed all those questions in on time and got them correct on your first or second try. Because of this late policy, I'm not going to hand out any extensions. No extensions. So if you wait until Sunday to do it all and realize, oh, I can't fit it in before midnight, I'll point you to that late policy. So remember, a due date doesn't mean you have to do it on that date. I do encourage all students, because we spent 2 weeks on chapter 1 to start that homework set as we move through the chapter. Again, midterm 1 practice exams are posted. And then finally, I will hold a review session in this room next week, next Thursday at 6 p.m. to 8 p.m. It's in this room, it's on Zoom, and I record it. This information is on our Carmen page already. It's in our calendar. I have a page about it under exam resources and all that jazz. This review session is actually open to all of Chemistry 1210 students, so that's 4,000 students who are taking Chemistry 1210. So I've invited everybody, so invite your friends. I do encourage you though to come via Zoom if that's what you prefer, because there is limited space in here. And of course I record it, so if you're busy on Thursday, no big deal, it will be posted. And you can expect that for every midterm and final exam. Yes. Okay. All right, let's move on to dimensional analysis. Again, one of the most important skills in the sciences, and it's just being clever with units, manipulating units. So, we showcased metric prefixes a little bit earlier. You all have those metric prefixes memorized, right? So now we're going to be using them, converting units and doing some more complex problems. And again, the skills I show you here will help you solve these more complex problems that aren't just straightforward, like, okay, convert meters to kilometers or something. So the whole idea of dimensional analysis is to cancel units by multiplying fractions. A fraction with a certain unit on the top and a certain unit on the bottom. So if you're given a certain unit and you want to get to a new unit, the idea is let's multiply by this fraction, this conversion factor, where the given unit is the same on the top and the bottom here, all right? So these two units will cancel out, and your desired unit is up top, giving you that new unit that you want. The skill that we're using here back from, algebra is if you have the same unit on the top and the bottom of a fraction, then they cancel out. And that's the whole idea, cancel out units top and bottom. So here's some other examples of conversion factors that come from this definition. Hopefully we all know that there's if in 1 dozen of something, there's 12 items. So here we have an equality. So what's great about this equality is that when I want to make a conversion factor, I can either put the 1 dozen up top, like in this fraction, or I can put that 1 dozen on the bottom, putting that 12 items up top. So notice how it's the same equality, it's the same relationship here, but I can put whatever unit I want either on the top or the bottom and make sure that appropriate number goes along with it. So this is the idea of converting units to another unit and canceling those units as you go, how we can manipulate these conversion factors from an equality. So let's look at this example where, okay, let's convert 5.25 meters to centimeters, all right? So the idea here is, okay, let's think of a useful conversion or a useful equality to help us get from one unit to another. We want to go from meters to centimeters. So do we know a relationship that relates those two things? A helpful conversion is 1 meter equals what? 100 centimeters, or if you're using that chart, I think they say 1 centimeter is equal to 1 times 10 to the negative 2 meters. They're both the same thing, all right? They're both the same conversion. So there's the equality we have to work with. So remember this equality, that equal sign, I can put either one of those things at the top and bottom of my fraction. So what I'm going to do is start with the value that's given. So 5.25 meters, all right? So I have a meter and I want to cancel it. So that means I have to put meter on the bottom of the next fraction. So if I look at my conversion, I'm going to use the top one here. I see that there's 1 meter in 100 centimeters. And so when you cancel out your units here, all right, meters cancel, we get that this equals 525 centimeters, all right? And that would be our answer, all right? So we're taking these equalities, turning them into fractions, getting those units to cancel appropriately. So the question is, okay, how many sig figs should my answer have? We learned about sig figs on Tuesday, and we see that all of the operations here are multiplication or division, all right? Multiplication or division. So what's the rule for multiplication division for sig figs? Lowest one wins, right? So just looking at all of those numbers I have multiplied and divided together, how many sig figs does it look like is the lowest? Looks like there's one, okay, but there's not, all right? There's a special case here that comes. So this answer actually does have 3 sig figs. This equality, 1 meter equals 100 centimeters, actually has infinite sig figs. So what's actually limiting us is the number we started with has 3 sig figs. And this was a question from the recitation packet that I'm going to clarify right now. And that's on the next slide, all right? So here are just some sig fig exceptions. And these are values that has infinite sig figs. So when a number has infinite sig figs, essentially we can just ignore that number in our sig fig calculations. We only want to use measurements to determine significant figures in our answer. Anything with infinite sig figs, like for multiplication division, any number is smaller than infinity, right? So anything with infinite sig figs we can ignore. So here are some examples of things that have infinite sig figs. Counting numbers, like 1 dozen equals 12 of something, or that in one day there's 24 hours. Those are counting numbers. Or a lot of the definitions that we talked about here. So 1 meter, 100 centimeters, or 1 milliliter is 1 centimeter cubed. In this definition, those numbers, it looks like there's 1 sig fig, but there's not. There's actually an infinite number where it's a definition, it's exactly 1 milliliter equals exactly 1 centimeter cubed. Let's recall what the rule is for significant figures. It's all of the digits we report in a measurement, or all the numbers we know for certain, plus 1 we estimate. So in all of these numbers up here, the counting numbers, the definitions, every digit is certain. There are actually no estimated digits, and that's why there's infinite sig figs. So really, 1 milliliter equals 1 centimeter cubed. It really should be 1.00000 to infinity is equal to 1.00000 to infinity. So these numbers actually have infinite sig figs, right? And so we can ignore them in calculations. So when I go back to this example of what we just did, convert 5 meters to centimeters, the only value that has a finite number of sig figs is that first number. This has 3 sig figs, but these numbers have infinite sig figs. So if we use our multiplication division sig fig rules, lowest one wins, which number is the lowest, 3 or infinity? 3, yes, so 3 sig figs will be in our answer. 3 sig figs, not 1 sig fig. These are infinite sig figs, so we ignore them. Right, so we'll see this a lot. When you see like an exact 1 number, we can essentially ignore the sig figs that come from it. It doesn't actually have 1 sig fig. It's 1 with an infinite number of decimal places. All right, so let's practice some dimensional analysis with conversion factors. So this is like practice with training wheels. I'm gonna hold your hand and we're gonna practice canceling out units appropriately, turning these equalities into conversion factors to appropriately cancel our units. So here's the question. Eggs cost $2.50 per dozen. There are 12 eggs in a dozen. How much will it cost to purchase 108 eggs? Just ignore sig figs for now, since we're talking about money. So the strategy, like any dimensional analysis question where we're using units to, or values to convert from one to another, you always want to set up your equalities that are either given in the question or equalities or metric definitions that you should have memorized. So I like to collect those equalities and write them out. So I've already done that for you. Again, this is an example with training wheels, and then we'll do one where I don't hold your hand. So here are those equalities given, okay, based upon the information given. Eggs cost $2.50 per dozen. So I wrote this equality that 1 dozen eggs equals $2.50. All right, that's my first equality that I can use. The next sentence is there are 12 eggs in a dozen. So there's my next equality, 12 eggs equal 1 dozen. And so now the question proposes how much will it cost to purchase 108 eggs. So the idea here is I'm gonna start with this 108 number first, and then multiply by the appropriate fractions to hopefully get to the unit of money at the end. So let's look at all of these equalities and the spots that we can put fractions. So right now we're starting in the unit of eggs. And I recognize that you could probably do this in your head. You could probably just do this on your calculator and get it. But the idea here is I don't want you to memorize, do I have to multiply or divide to get my answer? No, it's all about the units, all right? So if I'm in the unit of eggs right now, I want to put eggs in the bottom, all right? So which one of these equalities has the unit of eggs in it? The first one or the second one? The second one. Yeah, there's eggs everywhere, but this is dozen eggs, this is dozen eggs. So we actually want to put those 12 eggs on the bottom, right? So that means the other side of the equality goes up top, 1 dozen. Perfect. So if we multiplied this through, what unit are we in now? Dozen. So that means to convert to the next unit, I want to put dozen on the bottom. And so now let's use that last equality. 1 dozen eggs is $2.50, right? And so what you see here, eggs cancel, dozen cancels, and we're left with the unit of money, and I think the answer is $22.50 there in the corner, right? So yes, I recognize that this question is straightforward enough. You've maybe done this, on your iPhone calculator in the grocery store to figure out, how much money something's gonna cost. But recognize it's all about canceling units. I don't want you to memorize, do I have to divide or multiply by this number to get to my answer? It's all about those units, okay? Because there's enough stuff you have to memorize. Save that room for, more important things. All right, so let's do another one. Here, this one has to do with metric units. So I'm not gonna hold your hand anymore, but I still giving you a strategy here. Let's convert centimeters to kilometers, all right? So centimeters to kilometers. A centimeter is really small, right? It's like that small. A kilometer is really, really long, okay? Longer than my arms. But does anyone here know how many centimeters are in a kilometer? Okay, so maybe you have memorized it, but really you shouldn't, okay? Don't memorize how many centimeters are in a kilometer. When we looked at that metric prefix table, everything was related to the base unit, all right? A centimeter is really small. So the strategy here is let's convert centimeters to meters first, because I know that conversion. That's a conversion I memorized, right? We know that in 1 meter, there's 100 centimeters. Or, we can write 1 centimeter equals 1 times 10 to the negative 2 meters, same thing, all right? Either one of those. I know that conversion, right? So I can convert that centimeters to meters. Now let's think about our desired unit, kilometers. Do we know, again, I don't want you to memorize how many centimeters are in a kilometer, but what I do need you to memorize, and I already asked you to, is how many meters are in a kilometer. So the idea is relate everything to the base unit to get where you want to go. So we went from centimeters to meters, and now we're going to go meters to kilometers. So the useful definition or equality here is that in 1 kilometer, how many meters are there? 1,000, or 1 times 10 to the 3 meters. So these are the 2 equalities that I'm going to use in my fractions to get to my answer. So let's put this all together. So start with the value that's given here, and we're going to multiply by a bunch of conversion factors. So 3.70 times 10 to the 7 centimeters, multiply it by a fraction. So which one am I going to use, the top one or the bottom one, or this first equality or the second one? We're going to use the first one. Where is that 100 going to go? On the bottom, because we're in centimeters right now. Centimeters is going to go on the bottom to cancel it. So 100, and then 1 meter goes up top. But we're not done. If we finished right now, we'd be in the unit of meters. We got one more step to go. So let's convert that meter to kilometer. Again, I want to cancel out the meter. So I'm going to put that part of the equality on the bottom there. 1 times 10 to the 3, or 1,000, is 1 kilometer. Right, and so if you do that, you get a number like 370 kilometers. This should have 3 sig figs, so I'll just put a dot there. But you can write 3.70 times 10 to the 2 as well to be very clear that this number has 3 sig figs. And the reason is because the number that I started with has 3 sig figs. All right, because how many sig figs do each of these fractions have? Infinity, so we ignore them. All right, because 3 is smaller than infinity. And all of this is multiplication division. So what I would put in my calculator to solve this, all right, I mentioned the E button, the exponential button is very useful to kind of save time in writing this 10 times 10 to the exponent value here. So this is exactly what I'm going to put into my calculator. I'm going to put 3.7, you can put the 0, but you don't have to. E7, so that E button, at least on like a TI 83 or 84, is above the 7. It's above the 7, but you have to hit second to do it. So it's the EE button. So I'm going to make that EE button and then put 7. Remember, that E replaces times 10 to the, right? I don't have to multiply by 1. So instead of multiplying by 1, I'm actually going to, my next operation is I'm going to divide by 100. So instead of multiplying by a bunch of fractions, I'm just going to recognize if I have a number in my denominator, I can just divide by 100. Instead of multiplying by 1 over 100, I can just divide by 100. All right? Then the next operation, same idea. I don't have to multiply by that 1. Instead, since I see that non-1 number on the bottom here, I'm also going to divide by 1,000, right? And then that should give you 370 kilometers, all right? And so that's kind of the faster way to do it, that you don't have to put in these numbers and then do times, parentheses, a fraction, and then close the parentheses times another set of parentheses fraction. This helps you save time if you recognize how fractions work with multiplication division. All right, so there is another example. I promise it's going to get harder. And another one here. So let's convert like 1.5 liters to meters cubed, right? A liter is a volume. A meter cubed is also a volume, all right? It's just different ways of thinking it. Typically, like liters, milliliters, we talk about liquids, but we can talk about volume in terms of cubic lengths as well, right? So I already told you, do memorize that conversion. 1 milliliter equals 1 centimeter cubed. This allows us to kind of jump around the like liter realm, that liquid liter realm, to the cubic, that cubic volume realm, 1 centimeter cubed. All right. So my strategy here is, again, do not use up the valuable space in your brain to memorize how many cubic meters are in a liter. Do not memorize that. All right. Instead, we're going to use useful equalities and base units to arrive at the answer we want. So my strategy here is, okay, we're given liters, so I'm going to convert to milliliters first. I know that conversion because that's just a prefix. Then we're going to use that conversion we memorized, milliliter to centimeters. We know that's just a one-to-one ratio. And then finally, we're going to go to centimeters cubed to meters cubed. But that's the tricky one, all right? That's the tricky one. So let's go through this together. What is the useful equality that takes us from liters to milliliters? In 1 liter, there are 1,000 milliliters. Or if you're using that table, you can write 1 milliliter is equal to 1 times 10 to the negative 3 liters. You can write that too. I like to think, okay, a liter, think about like a 2-liter bottle of soda or something. It's like this much. A milliliter is like a couple drops, right? So there's going to be a lot of milliliters in 1 liter. And so if ever I wonder, okay, are my numbers correct? I just think about magnitudes. A liter is really big. A milliliter is really small. So there has to be a lot of milliliters in a liter. Right, so that's the conversion that'll help us make that first jump. The second jump is the one we have to memorize. 1 milliliter equals 1 centimeter cubed. And now the last one, centimeter cubed to meter cubed. Does anyone here know the exact conversion between cubic centimeters to cubic meters? I hope not, all right? Again, I don't want you to spend valuable space in your brain to memorize things that you don't need to. These units are cubed. So here's the trick, all right? Here's the trick. Do you know how many centimeters are in a meter? Yes, how many? So 1 meter equals 100 centimeters. So if we want to make the relationship between meters cubed and centimeters cubed, what we're simply going to do is cube both sides. That's it. That's it. So if we kind of expand that, remember this cube applies to the unit and the number. So 1 meter cubed. 1 cubed is what? 1. So 1 meter cubed equals 100 cubed centimeters cubed. All right? So there is 100 cubic centimeters in a cubic meter. Right? So I didn't memorize how many cubic centimeters are in a meter. Just recognize, oh, if I have to square or cube a unit, make that conversion, you just square or cube both sides. All right. Here's an example. Does anyone here buy mulch? Yeah. In what unit do you buy mulch? Yards. Yeah. So when you buy mulch, it's in a yard. So, but it's actually a cubic yard. All right, a cubic yard. But when you go to the store, and like if you go to Walmart and buy bags of mulch, they don't come in cubic yards, they actually come in cubic feet. So let's calculate how many cubic feet are in a cubic yard. So I don't want to save my valuable brain space to memorize that, but what I do know is that in 1 yard, how many feet are there? 3 feet. So based upon that, how many cubic feet are in a cubic yard then? What will we have to do? We'll have to cube both sides. So 1 cubic yard is equal to 3 cubed cubic feet. And so 3 cubed is what? 27. Yeah, so there are 27 cubic feet in a cubic yard. That's kind of nice to have in your back pocket if you buy a lot of mulch or rocks or something. All right. Yeah, so that's how that works. It works for any units. All right, so let's actually put this together now. We got those useful equalities. So now let's actually make that conversion. Let's pick a different color. All right, so let's start with 1.55 liters. We're going to use that first equality. 1 liter is on the bottom, 100 milliliters up top. Or sorry, 1,000. Next, we're in the unit of milliliters, so we're going to do 1 milliliter on the bottom, 1 centimeter cubed up top. Now we're in the unit of centimeters cubed. Now, since we're in centimeters cubed and we want to go to cubic meters, we're going to use this last equality here, all right? So centimeter cubed is going to go on the bottom. Put the number that's associated with that. So it's 100 cubed on the bottom, and then that is equal to 1 cubic meter. And that will be our answer, all right? So in my calculator, this is exactly what I'm going to write, 1.55. So in calculator, 1.55 times 1,000 times 1 divided by 1, so I'm not going to do that, times 1 divided by 100 cubed. And that's what my answer will be. Right, so again, what I did was kind of remove those ones from there and recognize any number on the top of the fraction, you multiply, any number on the bottom, you divide. Right? So there we go. So that one's a little bit more not as straightforward. I promise it's going to get harder. But again, if you drink my Kool-Aid here and recognize canceling units and collecting equalities, it'll hopefully come together. All right, a couple more to do. All right, so this is one of the kind of applications of dimensional analysis. You know, we grabbed a bunch of conversion factors and equalities from, you know, it was given in the question, or metric prefixes or definitions. But there's another way we can collect equalities too, and that's via derived units. So essentially what a derived unit is any unit that has a fraction in it. Okay, if you have a unit that has a fraction in it, that is also an equality, right? But we just have to know how to read it, right? So any unit with a fraction, what you're gonna look for is the unit in the numerator, and then the unit in the denominator gets an inferred 1, where that 1 is an exact number, so it has infinite sig figs. So here's an example, all right? Miles per hour is a velocity, that is a derived unit. So if you're traveling at 60 miles per hour, tell me, how many miles do you go in 1 hour? 60. There's an equality, all right? 60 miles per hour means that 60 miles equals 1 hour. So notice how I took the top unit and the unit in the numerator and the value. That goes on one side of the equal sign. And then the unit in the bottom, hour, gets an implied 1. Right? So any unit with a fraction, you can turn that into an equality in a fraction that you can play with just like any metric prefixes, right? So yeah, if you're going 60 miles per hour, in 1 hour you travel 60 miles. So here's another example that's not as relatable is density. All right, we can write that the density of something is 1.29 grams per milliliter, but we can use the same analysis there, where the top unit and value, so 1.29 grams equals the bottom unit with an inferred 1. So I'm going to take that milliliter and put it right here, 1 milliliter. So what density means, so like 1.2 grams per milliliter, what it means as an equality is in 1 milliliter of stuff, there is 1.29 grams of substance or sample there. Again, milliliter and centimeter cubed are the same, so we can also write 1.29 grams equals 1 centimeter cubed. Same exact thing. This is a super useful skill because we're going to be using derived units all the time because that oftentimes describes our samples, all right? So let's do this next problem here. It's a little bit harder, okay, but we're still using dimensional analysis. This time it's with derived units. Olive oil has a density of that and a purchase price of $7.50 per liter. How much does it cost to purchase 2,200 grams of olive oil? So everything that is in red is a potential equality that will be useful to us. So I really urge you not to skip these steps because it'll help you put together the all of the fractions and dimensional analysis in your work. So it just becomes one problem in canceling units and not just a bunch of little mini calculations. So let's use that density and write it as an equality. So how would we rewrite this density as an equal sign? 0.92 grams equals what? 1 milliliter, right? So there's an equality we can use. The purchase price is also an equality. So how could we rewrite that? 750 equals what? 1 liter. Yep, 1 liter. All right. So what are we doing here? How much does it cost to purchase 2,200 grams of olive oil? So I'm going to start with that number. So 2,200 grams. Right. So which equality should we use first? The first one or the second one? First one. Why? There's a gram, yeah. And so where are we going to put that 0.19 number? On the top or the bottom of this fraction? On the bottom, 0.92 grams is 1 milliliter. So technically, we divided by density. Okay, technically we're dividing by density, but you don't need to know that as long as you're canceling units. So you don't have to rearrange the density equals mass over volume thing to get what you want. No, you can just use units the whole way through. You can totally forget that density equals mass over volume as long as you're good with canceling units. All right, so we're in the unit of milliliter. What do we want to do next? So the last equality we have is liters to money, and we want to get to money. So we can't use this straight off the bat. What do we have to do first to this milliliter? Yeah, take it to liters. So I want a liter. So the relationship between milliliter and liter is there's 1,000 milliliters in 1 liter. Right, so that's a metric prefix you memorize. And then the last thing we do is use the money equality. So 1 liter is 750. And we're going to ignore sig figs here. Right, so notice what we did is we used the first derived unit density right there to turn the gram amount to a volume. And then we use the money conversion to turn it into money, which is, I think, $18 if you multiply that through. All right. Okay, so let's do some more. All right, so here, dimensional analysis also works if you want to convert the units in both the top and bottom of your fraction, so your numerator and your denominator. The idea here is you just have to convert those units one at a time. So the idea, like, think about velocity. We can report a velocity in miles per hour. That's what we understand. That's what's on our vehicles. But in physics, oftentimes they report velocity in meters per second. Right? So miles per hour, meters per second. Both of them are length over time. So the idea here is if you want to convert that velocity unit, you just have to convert each unit individually one at a time, right? We can convert miles to meters. We can convert hours to seconds. We just do them one at a time. So here's the problem, all right? And this is very similar to a homework problem. We're just replace Popeye with a goose, all right? Popeye, her top speed is 9 miles per hour, and she weighs 6 pounds. What is Popeye's kinetic energy in joules when running away from me at 9 miles per hour? So this is bringing back kinetic energy, right? We know kinetic energy of a moving object is 1/2 mv squared. But remember, equations are like vending machines. We can't just put whatever numbers we want in there. Mass has to be in kilograms, and velocity has to be in meters per second. But I didn't give you those units in the question, so we have to do the work and convert them. So that's the strategy here. But I give you a velocity. Here's her velocity, okay? And then here's her weight. There's her mass. So we got to convert both of those things, right? So let's do the easy one first. Let's convert mass first, all right? So let's convert her 6 pounds into what unit do we want to convert that to? Kilograms, yeah. Although I didn't say it in the question, it's because we are using that kinetic energy equation, which requires those units. We want to convert that pounds into kilograms. So I have some useful definitions for you here. We're going to use this one. So where am I going to put the 2.2? Top or bottom? Bottom. I'm going to put it on the bottom because that one has the pounds. And then I'm going to put 1 kilogram up top. So her weight is something like 2.727 kilograms. This should have 2 sig figs, but I'm going to be a good chemist and just keep additional digits at the end, but know that if I were done, I would round to 2 sig figs there. All right, so I'm just going to keep that on standby. Because now let's do the hard part, and that is converting miles per hour to meters per second. Again, because the kinetic energy equation requires that meters per second value. So again, strategy, we're converting miles per hour, meters per second. So the idea here is we're going to convert miles to meters. Both of those are lengths. We have all the information we need to convert those things. And we're going to convert hours to seconds, but just separately, all right, one at a time. So I'm going to rewrite this 9 miles per hour this way, 9.0 miles in 1 hour. Essentially what we're doing is converting the 9 miles to meters, and we're going to convert the 1 hour to seconds. We just do it one at a time. It doesn't matter which order you do it. So which one do you want to convert first, the top unit or the bottom unit? Top, okay. That's boring. I'd do the bottom one first, but that's just me. So, okay, we're going to convert the miles to meters. So let's look at these useful definitions that are given here. I'm going to use the miles to feet conversion. So I'm going to put 1 mile on the bottom, 5,280 feet up top. Cool. Now we're in the unit of feet per hour. But I don't want that. I want meters per hour. So what conversion should I use next in that useful definition box? Probably the feet to inches. Yeah, so where am I going to put the 12? Top. Yeah, so 1 foot on the bottom, 12 inches on top. See, we're never memorizing, oh, I need a multiply or divide by 12. See how there's no memorization here? It's all about canceling units. Okay, what unit are we in now? Inches per hour. So we want to get to what? Meters. So we're in inches, so let's go to centimeters. I'm going to speed this up. 1 inch, 2.54 centimeters up top. And then from centimeters, I want meters. So centimeters on the bottom, meter up top. The relationship there is 100 centimeters is 1 meter. Right? Okay. So if we finish right now, miles would cancel, feet would cancel, inches would cancel, centimeters would cancel. Our unit right now is meters per hour, but we don't want that. We want meters per second. So now the strategy is, okay, let's continue this question and convert that hour to seconds. But notice how hour is on the bottom now. It's on the bottom. But that doesn't matter in terms of canceling units. The idea here is let's convert that hour to seconds. But in this fraction, this red one that I'm writing right here, hour, that unit should be where on this fraction? On the top, because hour right now is on the bottom. So I want to put hour on the top, and I'm going to put, what's it, hour, minutes on the bottom. So in 1 hour, there are 60 minutes, right? But I'm not done. Now we're in the unit of what? Meters per minutes. I should put minute. Meters per minute, but I want meters per second. So I'm going to put minutes on the top again. Here, seconds is going to be on the bottom. So 1 minute is 60 seconds. And that's it. All right, yeah, so that's a very, very long question. But never did I memorize, oh, I need to divide by 60 or multiply by 60. None of that jazz. It's all about canceling units and knowing your equalities. So if you put that in your calculator, you get that Popeye's speed instead of miles per hour. In meters per second, she is traveling at 4.023 meters per second. Perfect, and now these are the numbers that we put in the kinetic energy equation to finally get the joule amount that we want. So this was the hard part, all right? Converting miles per hour to meters per second was the hard part. Plugging it into kinetic energy is the easy part. So kinetic energy is 1/2 per mass, 2.727 kilograms per velocity, 4.023 meters per second squared. All right, let's report out to 2 sig figs because all the numbers given were 2, and you get she has a kinetic energy of 22 joules. 22 joules. I'm thinking about getting ducklings this weekend or next weekend. I'm not sure. If I do, I'll set up a webcam so we can watch her or watch them. I think 3 of them. Okay, 2 more, I think, and then we're done. All right, so Dr. N has a lot of large and small engines to take care of on the farm. I collect motor oil in a large square-ish tote with these dimensions. Oil has this density. How heavy is this tote in pounds? Right? So here are the dimensions of the tote. So I can get a volume that way. So if I calculate volume, 48 inches times 40 inches times 46 inches, I get that the volume of this tote is 88,320, but what is the unit of this volume? Inches cubed, yes, because all of those are inches. Okay. So I want to know how much this weighs, so I'm going to be using that density. Remember, density is a derived unit. Rewrite this. Take the time now to rewrite it so you clearly understand that that fraction means that there is 0.88 grams of junk in 1 milliliter, right? So density allows us to go to a volume amount to a mass amount. I have a volume amount right now, but it's in the wrong unit. So my strategy here is let's turn that inches cubed to centimeters cubed, then to milliliters, and then I should be able to convert it and use that density. So I'm going to do that exactly. So I'm going to start with this volume. So 88320, is that right? Yeah, inches cubed. All right, and I want to go to centimeters cubed. But do you know how many inches cubed are in a centimeter cubed? No, I have no idea. But what is given in this question? Inches to centimeters, and that's what you need for this question. So I'm going to put the inch on the bottom and the 2.54 centimeters on the top. But is that done? No, what do I have to do? Cube both the top and the bottom. So both the top and the bottom. So what the bottom becomes is 1 inch cubed, so it's still 1. But the top one becomes 2.54 cubed centimeters cubed. Right, so this number is what you'd put in your calculator. So now I'm in the unit of centimeters cubed. Perfect, because now I can convert that centimeter cubed to milliliters. And now I can use that density. Where am I going to put the 0.188? Top or bottom? I'm going to put it on the top. Yeah, because 1 milliliter goes on the bottom, because that's the unit I'm in right now. And I'm going to put 0.88 grams up top. So technically, I multiplied by density. But again, I didn't know to do that because I memorized it. I knew to do that because of the unit, the derived unit itself, and how dimensional analysis works. All right, so that's a gram amount. There's its mass, but we want it in pounds, so we just need one more conversion. So let's use this useful conversion. Where does the 400 number go? On the top or the bottom? Bottom. Why does it go on the bottom? Because it's grams, and then we get pounds up top. And there's our answer. So it's about 2,800 pounds. I would need a class 2 hitch and trailer to move it. Sometimes we can give away oil, or sometimes people buy oil to put in their furnaces to heat their homes, right? Because technically oil is a fuel, and farmers do burn it, right? Okay, one more. Are we getting the hang of this? Are we memorizing anything? No, you're never memorizing anything. What are you doing? Just canceling the units and collecting those conversion factors and equalities like Pokemon. So let's do one more. The tire pressure in my car tires is 32 PSI. PSI stands for pounds per square inch. So let's express this pressure instead in grams per meter squared, right? So I'm converting this unit to a new unit. And the idea is we're starting with pounds per square inch. I want to go grams per meter squared. So my strategy is let's convert pounds to grams. We know how to do that, okay? We have the skills to do that. And then let's convert inch squared to meter squared. And we can also do that. We're just going to do them one at a time. So let's start with the number that's given, 32 pounds per square inch. So 1 inch squared. Which one do you want to convert first, the top one or the bottom one? Don't disappoint me. The bottom one, yeah, let's do the bottom one. Does it matter which way we do it? No, because it's all multiplication division. Yeah, so let's do the bottom one first. Let's convert inches squared to meters squared. So what do we need? I give you inch to centimeter. So 1 inch is 2.54 centimeters. But am I done there? No, what do I got to do? Square it. Yes, we're not going to use up the valuable brain space to memorize inches squared to centimeters squared. We're going to recognize that the regular conversion, if we just square both the top and the bottom, works the same way. So right now, I've converted inches squared to centimeters squared, but I want to get that to meters squared, all right? So I'm going to put the centimeter up top to cancel it with what's on the bottom, meter on the bottom. I know that conversion, 100 centimeters is 1 meter, but what do I have to do? Not cube it. Square it because this is area, not a volume. Yeah, so we're gonna square both the top and the bottom. Perfect, so there we go. 2 steps to convert inches squared to meters squared. So now let's just convert pounds to what? Grams. So I give you that there is that many pounds in a kilogram. So I'm going to put the 2.205, I'm going to do this in a different color. Let's do it in blue. 2.205 pounds is in 1 kilogram. So notice that now those two units cancel. I'm in kilograms, am I done? Nope, got one more step. Go to grams, so 1 kilogram is 1,000 grams. And then there is your answer, all right? I will show you exactly what I'm gonna put in my calculator, all right, to get this answer. I'm gonna do 32. 1 squared is what? 1, so do I need to multiply by 1? No, so I'm gonna do 32 divided by 2.54 squared times 100 squared. Do I need to divide by 1 squared? No, because 1 squared is 1, and divide by 1 is the same number. So I'm not going to do anything with 1. Then what am I going to do? Divide by 2.205, and then multiply by 1,000. And that's exactly what I will put in my calculator to get that answer. 2.2 times 10 to the 7 grams per meter squared. So that's a different pressure unit expressed differently. Yeah. Yeah, so the question was, can I just multiply by everything in the top and then divide by everything in the bottom? Yes, you can, because I think a property of multiplication and division, is this the right word, that it's commutable? Commutative? Okay, yeah. Which, what does that mean? You can do it in any order. Yes. I just do it by eye. I like to go up, down, up, down. But yes, if you did 32 times 100 squared times 1,000 divided by 2.54 squared divided by 2.205, you'll get the same answer. Why don't you just try it yourself and see? Yes. All right, so that is chapter 1. Chapter 1 homework is now going to be due on Sunday at midnight. Keep in your back pocket the Popeye question, because it's the same question in online homework. It's just with a goose. And a hint, there's a question about 2 spheres with the same mass. What is the ratio of the densities? Here's a hint. There's 2 ways to do it. The lazy way and then the math way. The lazy way is just make up values. Make up values for your diameters. Make up a value for your mass. And calculate the densities. Just make up numbers, all right? And then get that ratio. All right, so that's your hint. All right, so let's move on to chapter 2, right? So I'm gonna again emphasize to you, do grab the annotated slides because I'm gonna move through this chapter quite quickly. So we're gonna talk about atoms, molecules, and ions. So we're gonna talk more about chemistry stuff, not so much about numbers. But again, I spend a lot of time on dimensional analysis because I think it sets you up for success for the rest of your classes. I survey my students like every year and I ask them like, what's the one thing you remember from this class? And a lot of students say dimensional analysis because they thought, oh, I had to memorize all these equations and stuff. And once you recognize that equations are just dimensional analysis, you don't have to memorize anything. That's how I got through some hard physics classes. It's just be clever with units. All right, I'll point out there's some things to memorize in this chapter, particularly the ion names, formulas, and charges. So it's on slide about 30. So do memorize those now over the weekend because we're gonna hash those out next week and I'm gonna assume you know them all. All right, so what are we gonna talk about? We're gonna talk about atoms, elements, and naming. Oh, this is all messed up, sorry about that. We're gonna name some stuff. That's towards the end. We're gonna name different compounds. And when we get to that section, I'll try to be very clear that when we name things, we follow different rules for different substances. There's 3 different categories: ionic substances, molecular substances, and acids. And I'll show to you how to differentiate those things. But we got to talk about atoms and how historically we got to our current understanding of atoms and elements. You know, how did we get this periodic table? How do we know that it looks like this weird castle thing? How did we know to put the elements in this order? So a lot of really big discoveries were made. Many of these won Nobel Prizes. I forget which ones. I think all these last 3. This won a Nobel Prize. This one, Nobel Prize. This one won a Nobel Prize. Oh, I should do a different color. And then this one won a Nobel Prize, all right? Because with each of these discoveries, big changes in our current understanding of the world around us, it changed. So what we see is this evolution of what we thought the atom looked like. Because here's the thing. Remember in chapter 1, we talked about macroscopic, microscopic, and symbolic domain, right? Macroscopic is what we see. Can we see subatomic particles? Can we see atoms? No. So these scientists, they came up with these experiments and they discovered properties about something we can't even see, an atom. That's why they were notable. That's why they won Nobel Prizes. And that's why the model of the atom changed so much over time, right? So history of the atom. Right now, we're going to talk about this first row, the evolution between the billiard ball model, plum pudding, then the nuclear model. And then we're going to save what the real atomic model looks like for chapter 6. This is actually what the hydrogen atom looks like, but we're going to work our way through this first row. All right. So the first model, the Dalton's billiard ball model, is a very just simplistic way of looking at the idea of an atom, the idea that I can take a hunk of gold, cut it in half again, cut it in half, keep cutting it until there's a certain point where if I cut that object one more time, it's no longer gold. Really, this was more of a philosophical thing. Actually, back in like Roman and Greek times, sciences and philosophy really went hand in hand. And so this was kind of more of like a thought experiment, the idea that I could, take an object and cut it so many times, and at a certain point, it's no longer that object anymore. And that's what Dalton said, that all atoms are these individual, indivisible balls that you can combine with other things, separate, that they're of one element, they're always identical across everywhere on Earth. And so that was our kind of first idea of what an atom was, just like this non-breakable Lego piece of matter. What we'll see here is that our idea of the atom has evolved so much more sophisticated from this, but it was a good starting point. This was the model of the time for, I think, hundreds of years until subatomic particles were discovered. Because the idea is, okay, we have an atom, just a single atom of gold. If we cut it one more time, that single atom, what we're doing is actually cutting apart subatomic particles. And so it was once those subatomic particles were discovered, that's when Dalton's billiard ball model broke down. Right, so we're going to talk about the discovery of the very first subatomic particle, so something smaller than an atom. So I want you to think, remember, these people back then did not know what an electron was, what a proton was, what a neutron was. I hope you took sciences in some capacity and do understand that inside an atom there are protons, neutrons, and electrons. We'll talk about that soon, but let's look at the intricacies of history of, hey, these scientists did not know what they were. How did they discover what an electron was when you can't even see it? And here is the first experiment. In the mid-1800s, J.J. Thomson used the cathode ray tube to discover the electron. What is a cathode ray tube? It's essentially two metal discs, right, that we put inside an electric current and we plug into a wall and we energize it, all right? And so between those two plates, what J.J. Thomson saw was this mystery beam being emitted between these two metal plates. And I have that to demonstrate here in a second, all right? And so these were the different observations he made in this cathode ray tube experiment. I'll point out, this isn't some like crazy device. You've actually might have seen these prior. So, televisions now are like LED, OLED, LCD, like those types of TVs. But you ever go to like your grandparents' house or the basement of your house, you have those old TVs with the big backs on them, really big backs. Yeah, so those are actually called CRT TVs. They're called CRTs, meaning cathode ray. It's the same exact thing that I'm going to demonstrate right here. So let's look at the observations and then talk about that a little bit more. All right, so what he saw is this mystery beam was emitted. What he saw was that these mystery beams traveled in a straight line. He saw that they could be bent by a magnetic field, and I'm going to show that in a minute. I have to turn off all the lights. The ray can turn a pinwheel. The ray heats up when I energize it, and then what you saw is that the beam was always emitted no matter what the property, what metals he put inside this in this thing. So I'm going to demonstrate this. So here's my cathode ray tube. I have 2 metal plates, and I'm just going to turn it on, and this is energizing it. So it looks green, right? So when J.J. Thomson did this experiment, just so you know, it's a spoiler, electrons are invisible. But what he did was put a fluorescent screen so he could see this mystery beam, all right? So what do we see right now? This mystery beam is traveling in a straight line. What's the next thing? The ray, this mystery beam can be bent by a magnetic field. So I'm going to do that now. See that? Yeah. Is it bending? Bending? Yes, it's bending with a magnet, and actually from the, if I knew the polarity of this magnet, we could determine what the charge is of this mystery beam. So which way is it going? Is it going up right now? Up, up. So if I tell you that this is the positive side of the magnet, what can we tell about this mystery beam? It must be negatively charged because it's attracted. Or if I put the negative part of the pole here, what? Does it still fit that observation? Yeah, that if this is the negative side of my magnet and it's going away, it implies that this mystery beam is negatively charged. All right, what else? Bent by magnetic electric field. Okay, so there we go. So I'm going to turn this on. Okay, a little bit scary. Okay, so there's the cathode ray. This little apparatus is also a cathode ray, but there is no fluorescent screen here. Because I told you, this mystery beam is invisible. That glowing green stuff is just fluorescent so we can see the beam. So hopefully, maybe I should use my iPad so we can see this. So what's the third observation? The ray can turn a pinwheel. All right, so I'm going to show that to you now. So let me get my camera. Hopefully we can. Camera, where's my camera? Okay, all right. Do you see that, kind of? Yeah, see how it's not moving, right? Do you see those like little paddles? It's not moving, right? So what I'm gonna do is turn on my cathode ray tube. The mystery beam is going to go through it, and we'll see what happens. So what's happening? It's moving, so what does that imply about this mystery beam? It must have mass, and I wrote it for you, so I kind of scribbled it, but that's okay. So yeah, this ray can turn a pinwheel, so it implies that that ray has mass. What we see if we let this go, actually it's still spinning. It is still spinning in there. So the ray heats up, so it's highly energetic, and we see that all matter will do this phenomenon, regardless if we put iron, silver, gold as our cathode, it will do this phenomenon as well. And so the conclusion of this experiment is that this mystery ray is highly energetic, a negative fundamental charge of matter. What was J.J. Thomson observing? Probably. And we're talking about subatomic particles. If it's negatively charged, it has mass, it is an electron. So what he was seeing was an electron. All right, that's what we're seeing right now. Let me talk briefly about CRT TVs. So have any of you seen those TVs, played with them, and know what happens when you play with magnets close to those TVs? What happens? Yeah, so if you put a magnet to one of those old CRT TVs, it distorts the image, right? Just like we were seeing right here, because on a CRT TV, electrons are being emitted. Electrons are attracted to magnets, so when you put a magnet to these TVs, those old ones, you distort the image, just like we saw up here. Okay, all right, so that's the electron. Okay, so yes, J.J. Thomson discovered the electron. What else he was able to gather from this experiment was the mass to charge ratio of this mystery beam of light, all right? So that's important to note that this was a very archaic experiment, and so he could not determine what was the mass of one electron. He could not determine what is the charge of one electron, but what he could deduce from kind of a modified version of this experiment was the mass to charge ratio of this mystery particle, the electron. So this is important, and it'll come up a little bit later, that he was not able to get the single mass or charge of one electron, but instead the mass to charge ratio of an electron, and that's right here, all right? So he found out from this experiment that this mystery beam had a charge of, 1 × 10 to the 8 coulombs per gram. That's all he could gather from it. Until another experiment came around, and that's Millikan's oil droplet experiment. All right, so what we'll find out here is that the first subatomic particle that was discovered was the electron, and we'll see why, because all these experiments have something in common. So Millikan's oil droplet experiment, this is the setup. He took oil, he put it in like a spray gun, all right, took oil, sprayed it, okay, sprayed it so a bunch of drops were made. But then at the same time, when he sprayed his oil, he irradiated them with X-rays. And by doing that, those droplets were able to gain some negative charge to it, all right? So they were gaining electrons. Much like, have you ever rubbed your feet across the carpet and then touched something metal? What happens? You get shocked, because what's the purpose of rubbing across the carpet? You gain that static electricity. So that's essentially what he was doing to that spray of oil, right? So that's important, that the oil droplets gained negative charge, because oil, we know if we spray any liquid, what happens to those particles as time goes on? They fall, right? Because on Earth, we are all subject to gravity, okay? So at the same time, all right, all of this was happening at the same time. He would spray, he would irradiate with X-rays, and then he would turn on an electric field at the same time. And the point of that electric field was to attract that negatively charged particle upwards. So what's happening to this droplet is that gravity is pulling it down, and the electric field is pulling it back up. And what he was able to do was catch individual oil droplets, right, that were negatively charged when he turned on that electric field, right? Yeah, he was able to do that, and he did that a bunch of times, all right, where he caught individual oil droplets that were negatively charged. And from that, he was able to calculate the charge on each of those droplets that he collected. So he did this, hundreds and hundreds of times. From, the strength of the electric field that he turned on and the diameter of the oil droplet, he was able to calculate what is the charge of each of those oil droplets. And that is what's on the next slide. And this is what made Millikan a genius. Right? Did he win a Nobel Prize for this? I'm not sure. I don't think he did. I think it was too soon. Nobel Prize came around World War I. I don't know. I'm really bad with history. Anyway, so this is what made Millikan a genius, because he didn't just take all of the charges of each of the droplets and average them or whatever. He was able to look at this data and deduce the charge of one electron. But it's very subtle how we look at this graph, all right? Because we just see a lot of data. This is the data. This is how much charge each of the individual droplets had, right? There's a lot of data here. How can we interpret this? One way would be, let's just average all the numbers together. Nope, that's not going to give us the charge of an electron. What he noticed is that there was a reoccurring increment between all of his data sets. All right, all of his oil droplets. There's the same increment every single time. And so the idea here is that the oil droplet can only gain a integer number of electrons, like a whole number of electrons, all right? It can that oil droplet can have 1 electron, 2 electrons on it, 3 electrons, 4 electrons on it. And that's what he was measuring. So what's very important here is the increment, all right? This increment between all of his data sets, that is the charge of 1 electron. That was the charge, because he saw it keep reoccurring. Because the idea here is, okay, to go from this data set to this one, we gain 1 electron. 1 electron. 1 electron. That this electron is like a discrete thing that you can't gain a fraction of it, you have to gain a whole amount of it. And that's what made his experiment very, very powerful, that the most important information from this graph is not how tall the bars are. No, the most important information is the increments between each of those experiments. And it's a subtlety, right? So let me give you an analogy, right? Because this is a hard concept to get your head around, okay? So pretend that an electron is a lemon for a moment, and pretend that I sell lemons. And here's the problem for you. I don't know how much I sell my lemons for, but you have access to my cash register, and you notice these reoccurring totals from my cash register, right? So from my cash register, when I sell these lemons, I have a receipt for $1, $1.75, $1.50, $1.50, 50 cents, $1.25. From that data, can you determine how much one lemon probably costs? 25 cents. How'd you get that so fast? Yeah, so yeah, do we agree with 25 cents maybe? Yeah, 25 cents. Doesn't that work? Doesn't that work? So looking at this data, 25 cents goes into all of those numbers evenly, right? Right? Because can you buy, when you go to, Kroger, can you buy a half a lemon? No. Can a droplet gain half an electron? No. You can only, look at these in 5 whole amounts of lemons. So if we look at this data, yeah, a lemon probably costs 25 cents. So notice, what piece of information did we use to get that 25 cents? The smallest increment. Because some people might be sitting there thinking, oh no, if a lemon is 50 cents. But would that work here? If a lemon was 50 cents, which receipt total would be all messed up? The $1.75, because that means if a lemon is 50 cents, that means this person bought, what, 3.5 lemons? That doesn't make sense. Or the last person bought 2.5 lemons? That doesn't make sense. So it's not the smallest increment that is important. It's not the smallest value that's important, it's the smallest increment. And now if we go back with this information, we can determine how many lemons each customer bought. So this one bought 4 lemons, 7 lemons, 6, and then etc. All right, there's actually a homework problem just like this. Okay, but just replace the word lemon with wombombs. You'll know what I mean when you get to it. All right, so yeah, I'll go back to this graph. Again, the important thing is the increment. It's not necessarily this smallest amount, right? Because we don't know, is there 1 electron on this oil droplet? We don't know that. But what we do know is the smallest increment is constant here. All right. Okay, keep going. Perfect. Okay, so now that we have the charge to mass ratio from J.J. Thomson's experiment, and we have the charge of 1 electron from Millikan's experiment, now with these 2 experiments together, we are actually able to calculate the mass of 1 electron, right? Because what did we see from this experiment? This mystery beam has mass, right? So we can calculate what the mass of that 1 electron is with these 2 experiments, and it's really just dimensional analysis, all right? So from J.J. Thomson's experiment, he calculated charge to mass. So, 1.7 times 10 to the 8 coulombs per gram. Remember, let's pull out of our back pockets derived units and dimensional analysis. This value, what it means, because there's a fraction present, is that there's 1.7 times 10 to the 8 coulombs in 1 gram, because gram is on the bottom. Millikan's experiment determined the charge of 1 electron. So this definition means that 1 electron has 1.6 times 10 to the negative 19 coulombs. So to calculate the mass of 1 electron, I'm going to use those 2 numbers as conversion factors. 1 electron, let's cancel with Millikan's, oh, I spelled that wrong, whatever. Millikan's experiment, that puts us in the unit of coulomb. Then let's use J.J. Thomson's experiment that had coulomb per gram. Coulomb's going to go on the bottom, gram up top. This is just like chapter 1, okay? And then what we get is a tiny, tiny, tiny mass of an electron, right? When you put that in your calculator, we are able to get from these 2 experiments that an electron weighs a tiny, tiny bit of a gram. So times 10 to the negative 28 grams, right? So that's the important thing. So Both of these experiments together had to be developed in order to fully understand what an electron was. That we needed both J.J. Thomson and Millikan to get the full charge of the electron and its mass of this one electron, right? Okay, so yeah, one experiment without the other would have meant nothing. All right, so so this class ends at 10:55. I thought it ended at 10:45 last time, so I still have 10 more minutes. All right, so let's talk about the next development of this idea of subatomic particles. I didn't bring in my next demo. I'll demo something again on Tuesday about radioactivity. But so here's the thing. All right, we just discovered electrons exist. What does that mean about Dalton's billiard ball model? Is that true? Does Dalton's billiard ball model include electrons in it? No, so that means Dalton's billiard ball model is wrong. And that is how scientific progress happens, that we have these models that we think, match what the observations we see, but then, some crazy experiment and observation is made that goes against what the current model is. So the model must change, and that's exactly what happened. Once electrons were discovered, Dalton's billiard ball model had to change. And so the new model was simply called the plum pudding model, which includes electrons, all right? So what the plum pudding model is they said, okay, instead of just like an indivisible billiard ball that can't be broken up, let's just dot it with electrons, with small negative charge, okay? Let's just put dots in it. So, this was made in England, so where they eat plum pudding, I guess, where there's, raisins and stuff in it. So really think of this model like a chocolate chip cookie, where each of your chocolate chips are negative electrons, right? So now this plum pudding model includes electrons. But here's a thought, a subtlety. If we include electrons in this model, remember an atom is completely charge neutral. So if there's negative charge, what must there also be? Positive charge in order to cancel it out. So this is where the plum pudding model has the negative electrons as the chocolate chips, and then like the cookie part of it is this positively charged thing, all right? And that makes it overall charge neutral. And that's what I have down there, right? That the atoms are overall charge neutral, so if there's negative charge present, there has to be positive charge present. And so that's why there's both negative and positive charge in this plum pudding model, right? This still isn't what our modern day atom is, so that means a bigger experiment had to come about, and that's exactly what happened. And that is our third experiment, the Rutherford gold foil experiment. All right, but I have to talk about radiation for a moment. All right, so you'll talk more about radioactivity in Chem 1220. Who's going to take Chem 1220? Who's going to take it with me? Maybe. Okay, all right. I won't. You don't have to. It's fine. You don't want to. Different types of radiation sources that come from radioactivity, and I'll demonstrate that on Tuesday. These are what you need to know. There's three main types of radioactive substances or radioactive particles that can come off of substances. They are alpha particles, beta particles, and gamma rays. All right? Notice the language that's used here. Alpha and beta are particles, so they both have mass to them. All right, so if I took a ray of alpha particles or beta particles to this pinwheel, what would happen? The pinwheel would turn, it would spin, yeah, because they have mass. What about a gamma ray? If I took a gamma ray gun to that pinwheel, what would happen? Nothing, because there's no mass there, all right? So notice the language. So we can talk about mass, but we can also talk about charge. Alpha particles are positively charged. Beta particles are negatively charged. Alpha rays are just pure energy, no mass, no charge. So if we look at how these different radiation sources respond to a magnetic or electric field, we can see it's related to their charges. Notice how a beta particle is attracted to the positive side of your plate. Versus what should this red beam be? What is that? Probably alpha, because it's attracted to the negative side of the beam because alpha particles are positively charged. And then that gamma ray goes straight through. Why does the gamma ray go straight through? It has no what? Charge. But does this experiment say anything about the mass of a gamma ray? It does not. It does not. You'd have to use a pinwheel. That's a hint. There's one question on online homework that does poorly because of that idea. Okay. And that's what I have the answer down here. Which radiation source can turn a pinwheel? It's just alpha and beta. Gamma has no mass, right? No mass. All right, so we'll talk more about those. I'll demonstrate those radiation sources next week. Okay, so how did Rutherford use these radiation sources? Well, he took a substance that was a very good emitter of alpha particles, okay? What are the properties of alpha particles? They are what? They are what kind of charge? Positive, and then do they have mass? Yes, they have a ton of mass. So what he did is he basically set up this box that acted like a alpha particle gun. And he shot all of this stream of alpha particles at a very, very thin film of gold foil, all right, gold foil, so like gold atoms. Gold atoms where he was able to get that film to be only 1 or 2 atoms thick, right? So here's the thing. At the time, they thought that the plum pudding model was correct. The plum pudding model says, oh, atoms are uniform, okay? So what he thought is, okay, the foil is so thin that if I shoot these alpha particles through the foil, all of them should just blast right through that gold foil because the foil was so thin. That's what he thought, because at the time, the plum pudding model was kind of the model of choice. He thought that they would all blast right through, right? But that's actually not what he saw. So what he saw is that, yes, the majority of those alpha particles shot straight through that really thin gold foil, but just every so often, one of those alpha particles would shoot back. It would bounce back off of the gold foil. That's what you see, these different kind of diffractions off of the gold foil that they would bounce off. Even sometimes he would shoot the alpha particle and yeah, it would go straight backwards, back into the detector, right? This is essentially what he saw. It would be like if you took a piece of tissue paper and you took a gun and shot that tissue paper, what do you think would happen? It would go right through. That's what Rutherford thought. But this is what he saw. Every so often, he would shoot that tissue paper and it would bounce back at him. Isn't that crazy to think that you could shoot a piece of tissue paper and it bounced back? So that means our current view of the atom, the model for the atom, is incorrect. If those alpha particles shot back, what that implies is that there's something really, really, really dense inside an atom. That an atom is actually mostly empty space. But because some of those alpha particles scatter, we now know that nearly all of the mass of our atom is actually in the center of the atom. Okay? So remind me, what is the charge of an alpha particle? It is positively charged. So if I have this mystery thing that an alpha particle is bouncing off of, what should the charge of that mystery thing be? Also positive, because if that mystery thing was negative, would it bounce back? No, it would probably stick to it, right? So we actually deduced 2 things. We discovered the nucleus, that every atom has this really dense nucleus at the center of the atom, right? And we determined that the nucleus is what charge? Positive, because those alpha particles bounce off, all right? So that's what we were able to deduce from that the atom is mostly empty space. It has a very, very dense nucleus, right? They discovered protons similarly, all right, off of a hydrogen atom, but we don't really need to know that. So a lot of our work is mostly about the electron, but they did discover protons in a similar way to the CRT experiment. The neutron was discovered last. Why do you think the neutron was discovered last? What do all of these experiments have in common? Something about charge. What's special about a neutron? It has no charge. That's why it was discovered last. Not as important. Next week we will talk about atomic symbols, actually add protons, neutrons, and electrons, and how they're configured in our atoms.